Hello everyone and welcome to ML Done. In the last video we talked about gradient descent and what it really means. We said that if we have an error function with a certain mathematical formula, we could use gradient descent to compute the direction of steepest descent in the value of that error. So for a given neural network with a certain values for the weights, gradient descent helps us realize that. How should I change, meaning increase or decrease each one of those weights so that the error would go down the fastest? Now, in this video, we will go over the mathematical representation of everything that we've talked about. So, without further ado, let's start. So, we said that for a neural network, when we generate the outputs from using the training data, we would generate some outputs with certain deviations from the ground truth, meaning that we will have some errors in our prediction, right? And we would use that error to define how we should change our weights. Now, the way we would change our weights is going to be discussed here, but the value that we are going to compute is going to be represented by delta W, right? So whatever the old value of my weight is, let's call this guy the old value, right? I'm going to add the delta W value to it, and that would be the result for the new W. And you notice that we have that vector symbol on top of these weights, because your weight vector is a collection of many weights, as we talked about before. So W0, W1, all the way to W a gazillion. I mean, doesn't matter. We just consider a whatever number it is. So gradient descent helps us to adjust these weights, no matter how many of them you got. And we said that this delta W can be calculated using gradient descent in this shape. So for our error, which is a function of our weights, we would compute the gradient of that error with respect to each and every one of our weights, W0, W1, all the way to WK, whatever, right? And then we would multiply that value by eta, which is our learning rate, and we said that we need to negate this whole thing by 1 minus here, as you can see over here. And that's very important because we said that gradient by definition finds the direction of steepest ascent, not descent, ascent. So by negating that direction, we are looking at the direction of steepest descent because we want to minimize that error. Perfect. Now, let's take a look at this very simple neural network. So this is our bias unit, x0, which is always equal to 1. This is our actual input data, which is, you could think of it as a one-dimensional training data. We got weights, W0 and W1, that we are going to initialize randomly. And this blue circle over here is a neuron. And this line over here represents a linear neuron, meaning that the input and the outputs will be identical, right? Because of that, we call that a linear neuron. Now, we got the output of the neural network over here represented by O, and ultimately we will compute the error of the network. And then using that error, we will compute the gradient with respect to W0 and W1, and then update those values, okay? Now, one thing that I need to mention here is with respect to that letter Z, the symbol Z, that's an important one because as you notice, W1 is multiplied by X, and W0 is multiplied by X0. Remember, X0 is always equal to 1. That's the bias unit. So by this multiplication and then summing the results up, we get this Z. right? So this Z is nothing but the input to your neuron, and O would be the output from that neuron. And because it's a linear unit, O and Z will be equal, okay? And you can think of Z as a linear combination of the input and the bias unit using weights. Last but not least, this Z has a name. It's also called, because it is what the neuron receives so that it could get activated and produce your output, right? So this is our simple neural network, okay? Now what we're going to do, we are going to derive our mathematical formulas for, and ultimately derive the learning rule for the weights based on this neural network, okay? So 2 weights, 1 bias unit, 1 input data, and then your Z, your output, and the error, okay? Now, let's define our output as w.x. Now, why is that? Because your Z is already a linear combination of your weights and your x, right? And if you recall, your W vector is nothing but your W0 and W1, yes? And your X vector is nothing but your X0, the bias, and your actual training data, which is X1, right? Now, when you do the dot product, what it means is multiply, let me choose another color, it means multiply W0 by X0, and then plus W1 by X1, right? This is actually the same definition of as your Z, if you remember, over here on the top, right? But because it's a linear unit, your output will be equal to this Z, meaning that the neuron doesn't change anything. So because of that, I've changed this Z to O, right? Which is your output. So with vector notation, and this guy right here, this little dot, we call this the dot product, we can show this whole mathematical operations in a nice, concise way. Perfect. And finally, let's define an error, okay? Remember, the error that I'm gonna show right here, well, I've actually shown it already, it's called the sum squared error, right? So it's called the sum squared error, right? And there is a very good reason why we've chosen this error function, but this is beyond this video, all right? However, there is a Bayesian justification for this, okay? But we're not going to get into that. For now, let's just accept that this is a proper error function. Now I'm going to tell you what this error function really means. First foremost, you notice that the error is a function of the parameters of your neural network, meaning that it's a function of your weights, right? And your T of D represents the ground truth. These are the actual labels in your training data. So for every data, you have a label that you can compare your output with. And O, as we said earlier, is your output. Now, let's say that your entire training set is represented by D. So let's call this your training set. Meaning that you've got a bunch of X's, one-dimensional values, and for each one of them you have an actual ground truth. And the way we will go through this training set would be with this little index over here, small d over here, T of D, Os of D, right? So what does this mean? It means that And I think that we've actually talked about this in the previous video. But what this means is, for every, let's say we have a neural network and we have initialized our weights randomly. So the W's have been generated, right? So we will pass each and every data in our training set. So every X of D will be passed through our neural network, right? From here, over here. Right? So what would happen, we would compute Z, W1x plus W0x0. We would compute O, which would be equal to Z. Then we would use this error function to compute the error. But remember, error is nothing but a measure of distance between your output and the ground truth. This guy right here, the ground truth. So how do we measure that distance? So what we're doing here is T of D would be the output for, the ground truth for the XD training example in your training set. So that is, so T of D is what we would like our neural network to generate, to produce as the output. However, it produces something else most of the time, and that is represented by O sub D. Yeah? Now, O sub D is the output of the neural network if X of D was the input, right? So if you think about your neural network, yeah, X of D gets in, you generate O sub D, you have your ground truth for that example, which is D sub D. Then you measure the difference between these two, right? How do we measure? We say T sub D minus O sub D, and then we square it. Again, there is a good reason why we square it. There is a good reason why we have this 1/2 over here, but we're not going to get into that for now, okay? So we square that difference. That's why we call this the sum squared error, right? Now, we would do this for every training example in our training set, capital D. And that's why we have this sigma sign over here, right? So for every example in our training set, for every X of D, we would generate the outputs for every one of those examples, and we would measure this difference with the corresponding ground truth for that training example. We square it and we sum all of these values across the training set. And ultimately, after we summed everything, we would multiply the result by 1/2. And that would be what? That would be your error, your current error, given the current values of your weights. Remember, you've initialized these weights randomly, okay? And then using that value of the error that you've computed, you will learn the gradients. And then from the gradients, you will learn how to change W0 and W1 so that this error that you've computed so far would reduce the fastest. So we're gonna grab this entire error function and we're gonna compute the gradient of this error function with respect to our weights. We're going to show that with Wi. In this case, we have W0 and W1, right? So let's dig into that. Right, so the derivative of the error with respect to Wi, as we said, this is the entire error, right? So this chunk over here is our error. We're taking the partial derivative of this entire error function with respect to our weights Wi. Okay? Now, I'm going to walk you through the steps step by step, okay? So, the first rule that we've used here, as you notice, we have inserted the partial derivative operation inside the sigma. As you can see, we put it in. There's a very good reason for that, and it's a rule from basic mathematics. The derivative of a sum is the sum of derivatives. What what do I mean by that? Let's say we have this function. Let's say we have this function called f, and it's defined as xy plus x2, right? And let's say we want to define, compute the partial derivative of our f with respect to our x, right? So it means take the partial derivative of this entire function xy plus x2 with respect to our x. See how we do that. Just if you know how to solve this, just pause the video and try to solve this on your own. I know it's basics, but trust me, if you can do this, then the equation on the left hand side will be a piece of cake. So we take the partial derivative of the first part with respect to x, which is y. Notice we have the plus here, and then we take the partial derivative of x squared with respect to x, which would be 2x. So what happened? We had a partial derivative of this entire sum, but what we did was we broke it into two pieces. What we did was, actually, we took the partial derivative of xy with respect to x plus the partial derivative of x squared with respect to x, right? So we sort of distributed this derivation operation inside the sum. And that is why we have the same story over here on the left-hand side. So as you can see, we got the sigma outside, and then we got the partial derivative operation inside, right? And 1 over 2 obviously is a constant, so we don't even bother with that during the partial derivative operation, right? So what's the next step? Now we have the partial derivative of this section with respect to our weights. Now, let's see what would happen next. I know, looks scary, but trust me, it's not. So the idea is that we want to take the partial derivative of this guy over here with respect to w sub I, right? Now, what we've done here, we've used this another actually very cool rule in mathematics that we call the chain rule. This is an amazing achievement in mathematics, actually. Amazing. Now, what does chain rule say? Let's say we have a function called f. I'm going to define it with u to the power, let's say, k. And let's say that u itself is also a function of some other variable called x. Let's call it x to the power, just for simplicity. Well, actually, let's be more general. Let's just put an index, x to the power I, right? Now, we know how to define the partial derivative of f with respect to u. That's simple math, right? So the partial derivative of f with respect to u, k comes down, u to the power k minus 1, right? So this is basics. And we also know how to do this with u, right? So the partial derivative of u with respect to x, remember, k and I are just numbers, they're just powers. With respect to x, again, would be I multiplied by x to the power I minus 1, right? So this is easy, but the question is, what if we wanted to compute the partial derivative of f, not with respect to u, but with respect to x? As you can see, f is not a direct function of x. It's a function of u, and then u is a function of x. So how can we do that mathematically? Now, the chain rule says f is a function of u, right? Yes, it is. So first define or compute the partial derivative of f with respect to u that we have computed up here. multiply that by the partial derivative of u with respect to x. And we've computed that here too. And multiplying these results together would give us the partial derivative of f with respect to x. Now, let's just think what we're doing here. We're saying that what is the rate of change of f if I changed x just a teeny tiny bit? And the chain rule says if you compute the rate of change of f with respect to u, and then compute the rate of change of u with respect to x, and multiply these two quantities together, the result is the rate of change of f with respect to x, meaning that how much will f change if I changed x just a little bit, right? So these are all definitions. So the chain rule, the name actually is more clear now. The chain rule is a chain rule because we are chaining these mathematical quantities together. First this one and then that one, and depending on the functions that you're solving, the chain could go on. Okay. So what's happening here? So I'm focusing on this chunk over here, right? Taking the partial derivative of this guy with respect to w sub I. First, according to the chain rule, we will take the partial derivative of this guy with respect to t sub d minus o sub d. That is why 2 comes down. We repeat t sub d minus o sub d, and then we subtract 2 minus 1, which is 1, and we're not writing it here. So that 1 would be the power of this expression. Okay? And the next step is we will compute the partial derivative of the base with respect to w sub I. Okay? So what happened there? Again, we have this entire t sub d minus o sub d squared, right? We want to take the partial derivative of this with respect to w sub I. Now, if you consider this entire thing as, for simplicity, as u, it's as if you have u squared and you want to take the partial derivative of this guy with respect to x, right? So first step is you will take the partial derivative of u squared with respect to u, and then you take the partial derivative of u with respect to x. With respect to x. Or actually, in our example, it is not x, it is w sub I, or your weights, in other words. So this base over here is called u, right? So what do we do here? U squared with respect to u would be 2u, and that's this part. And then we take the partial derivative of u with respect to w sub I, and that's this part. Right? So that's your chain rule right there. I know the notation might seem a little bit confusing and cluttered, but trust me, that's just your simple chain rule and nothing more. So now we're going to look at the derivation of this last chunk over here, the partial derivative of td minus od with respect to w sub I. But before we go into the detail of this part, let's appreciate the fact that your o sub d, which is the output of your neural network, is nothing but the multiplication of your w's and your x's, right? So that is what we defined earlier, if you remember, over here. Your output is nothing but the dot product of your weights and the x's, w0, x0, w1, x1 in our simple neural network. Okay, so we're gonna denote o sub d like wx sort of dot producted together. Actually, I just had to add this little d over here because we're sort of going through the sum. We're going through all our training examples. So this is in particular the dth example. right? So for every x in your training data, you are computing the O sub d with the dot product of w and x of d, right? So now it's more clear, right? The partial derivative of this guy with respect to w sub I is far more clear right now. There we go. So let's pay attention to the fact that this 2 with that 2 have been simplified. TD minus OD is there, but the partial derivative of this chunk with respect to W sub I, how did it result this value? Can you understand what's happening there? Feel free to pause the video and dissect this in more details, but for those of you who just want to see how this has been computed, so the partial derivative of d sub d minus w dot x sub d. First of all, d sub d is not a function of wi, it's just your ground truth label. So the derivative of that with respect to w sub I would be 0. So all you're going to end up with is going to be the partial derivative of your weight vector multiplied by the dth example. Well, by multiply I mean dot product with respect to w sub I. Now, you have to pay attention here. This is where actually computing all of these derivations by hand becomes a little bit tricky. Remember that w1, for example, in our training example, is connected to your x, right? And w0 is connected to your x0. In other words, if I change my x, w0 will not be changed, will not be affected. Only w1 is on the way, right? So w1 and x are mathematically dependent on one another, but w0 is not. Now, why did I mention this? Simply because if you have the dot product of a bunch of weights and a bunch of x's, the only x actually that you're interested in is going to be the ith example. So what do I mean by that? So we're basically ignoring all other x's. We're just considering, so we're still talking about the dth training example, but we're only considering the ith dimension of it. Now, if I want to make this more clear, I'm gonna expand on the dot product and show you what I really mean behind the scene, like as to what's happening. So if the dot product, if I expand on the dot product, then I see something like this: x0 plus w0, sorry, x0 multiplied by w0 plus w1 x1 plus w2 x2, and so on and so forth. Let's say I want to take the partial derivative of this whole expression. Remember, this is my output basically, with respect to just w1 and no one else. What do? The first expression has nothing to do with w1. So the derivative of that with respect to w1 is 0. The third expression also will be eliminated. Every other expression will be eliminated because it's only this part that's a function of my wi, of my w1. Yeah? So the partial derivative of this entire thing with respect to w1 is actually the partial derivative of w1 x1 with respect to w1. And that is equal to x1. Right? That is why you can see that only the x's that have the same index as your w has survived. So because we are taking this derivative with respect to w sub I, because of that, only the expression, the x that has the same index, in this case x sub I, survives. Right? And this final thing that we've computed here is your gradient is your gradient with respect to the weights of your neural network, right? So if you think about it, again, according to what we discussed earlier, your gradient is nothing but a vector of gradients. So we got with respect to W1, then we've got the partial derivative with respect to W2, all the way to whatever weights you have. Let's call it WK, right? So you compute that this value, this gradient with respect to every one of your weights in your network, and that results in the gradient vector, this entire monster over here. So if I want to just read this out loud as to what it means, it just means that in order to update my W sub I will generate all the outputs of the network for all of my training examples. I would measure the difference between these outputs and my ground truth, and I multiply that with my x sub I sub d, meaning that the ith dimension of my dth training example, and put a minus value there. If I sum all of these values across all my training examples, only then will I get the ultimate value, which will tell me how should I change my W sub I so that my ultimate error would go down the fastest. So this is exactly what I talked about. So the delta W that you're going to compute, as I said, is a multiplication of your learning rate and minus the learning rate multiplied by your gradient. And as the gradient is this giant vector over here, we will multiply our eta with by the element of our gradient vector that is corresponding to W sub I. So it's only this entry that is of our interest, because we're only interested in updating W sub I here. Okay, so minus eta multiplied by the only entry of our gradient vector that is corresponding to W sub I. So what does this mean? It means compute the rate of change in error with respect to W sub I and multiply that minus the learning rate. That will tell you how much you have to change your W sub I in order to minimize the error the fastest. And since we computed that this is the gradient of the error with respect to W sub I, with simple replacement, we get this entire expression, right? So we can actually get rid of this minus with this minus over here, so they will cancel out. And this, my friends, is the amount of change that you need to apply to W sub I so that you would minimize the error the fastest possible, the fastest way possible. I know that there are so many notations, so many expressions, indices and everything, and you might not have grasped the idea as well as you had hoped. But in the next video, I'm gonna actually do this with numerical example. With a numerical example, we will actually go through our neural network. We would pass our training data one after another in. We would compute the outputs and the errors. And then we would compute these gradients for the same values. And ultimately, we will update our weights. So the weights will be updated like that. So for W sub I, the new W sub I would be the old W sub I plus our delta WI, which we have computed over here. Perfect. So I hope that this has been informative for you. It certainly was fun to make, although it might have been a little bit confusing, but bear with me. In the next video, things will fall into place. But in the meantime, I hope that this has been informative for you. If you like the video, feel free to subscribe to my channel. And if you have any comments, you're more than welcome to write them in the description. And if you're interested, you can connect with us through the Twitter, LinkedIn, and the Facebook account of MLDon. And the website is also mldon.com. And finally, I'm going to post a link to the blog post that I've created on mldon.com for this very video. So for those of you who'd enjoy a more written type of lecture, that will be also available for you. So in the meantime, mind yourselves. On behalf of MLDon, take care.